All right, we're going to be continuing our discussion of bioenergetics and metabolism. This time, our learning objective is to explain how changes in Gibbs free energy determine the direction of chemical reactions. Now, as you recall, delta G is a measurement of energy that is needed for a reaction to occur or is gleaned from a reaction. So if delta G is negative, it means that it is thermodynamically favorable. It's a process that is likely to occur, and consequently, the reverse of this process is not likely. This also means that that negative delta G, that energy, is available to do work. Conversely, if we have a positive delta G, it's thermodynamically unfavorable. In fact, the reverse is favorable. And if we have a positive delta G reaction, it means that energy is required for this to occur. Okay? Something that we don't usually talk about is when delta G is zero. So when delta G is zero, there is no net gain or loss of free energy, but this particular reaction is readily reversible, so it can run in both directions. And this occurs when your reaction is at equilibrium. So let's take a look at how we calculate delta G. Of course, it all comes down to this equation right here. So the Gibbs free energy, or delta G, is equal to the change in enthalpy minus the temperature times the change in entropy. Something to think about is we can gain energy from changes in either one or both of these characteristics. So we could liberate energy from a molecule by breaking it apart, taking the energy out of those bonds and putting it into the free energy category, or we can take something and make it more disordered. And we can gain energy from either one of those changes, or as I said, more commonly, a combination of both. And something that I want you to recognize here is that the temperature of a system is directly impacting the entropy of a system. And if we think about this from a standpoint of temperature is merely a measurement of the kinetic energy in molecules, so how fast they are moving around, we can see why this would impact entropy so much. Because if we're looking at things bouncing around and dispersing or spreading out, the faster that happens, the more of a change you're going to see. So when we think about delta G in terms of reversible or irreversible processes, this is where we start coming back to the idea of equilibrium, or the idea of having a zero delta G type of scenario. So this is a reversible process, right? And a perfect example of this is ice melting at 0 degrees, right? Or we could have ice forming at 0 degrees. It can be going either direction, right? There's no real gain or loss that's occurring there. And what we'll find is there are actually quite a number of chemical reactions that are occurring at equilibrium. Consequently, irreversible processes are those that are far away from this equilibrium state. An example of this is burning paper. When you have a sheet of paper, it is very far away from being carbon dioxide, right? And when you burn it, it is now, as CO2, very far away from being a piece of paper. And this is where we have reactions that are either going to glean a lot of energy or require a lot of energy. Now, if we start looking at the individual contributions that we might have in a particular reaction, we could have a reaction that has a positive delta H, right? So a positive change in enthalpy, so it's absorbing energy here, but also a positive change in entropy. This is going, since it is minus temperature times entropy, a large entropy change would result in a negative delta G. When we look at this in regards to temperature, at a low temperature, this delta G is positive and not favored, right? Because if the low temperature is low, then we have a low multiplier on this entropy change. At high temperature, the multiplier effect of temperature times entropy is going to give us a large negative delta G, so consequently it's favored. So if we look at these different situations here, so if we have a large gain in enthalpy, but a loss in entropy, regardless of what temperature it is, it's not favored. Conversely, if we have a loss in enthalpy and a gain in entropy, it doesn't matter what the temperature it is, it's favored regardless. And again, if we were down here and have a loss in enthalpy, but also a loss in entropy, this is going to have a strong temperature affected scenario. So at low temperature, it will be favored because the low multiplier is minimizing the loss of entropy. But at high temperature, it's not going to be favored, and delta G is going to be positive because of the multiplier effect of temperature on this problematic loss of entropy. So when we look at different equations, we will see different amounts or different effects contributing to the ultimate outcome, right? So here we have fermentation of glucose to ethanol here. This is going to cause the liberation of some gas. So something to consider here, that this one molecule has now become four molecules. Okay, that has more entropy, right? In addition, you're going from a solid to liquid and gas phase, which again is more entropy. So this reaction has a large entropy change, right? And this is really giving it the bulk of the energy, but we are still liberating some energy from the bonds itself. Now, if we look at the combustion of ethanol, um, this is a slightly more complicated scenario because you are going from um, one liquid molecule and three gas molecules. You're now going to two gas molecules and three liquid molecules. That is kind of the opposite direction of entropy, right? Because if you're ranking materials based on solid, liquid, gas, solid is very low entropy, gas is very high entropy. So we're taking a hit there, but the overwhelming change in liberation of energy from those bonds itself, that change in enthalpy, still makes this a net negative delta G reaction. Here's a slightly different scenario where we're looking at decomposition of nitrogen pentoxide. So here we have N2O5. Again, this is a solid. We are going to two molecules of gas, and this is part of a half reaction, so we're getting half of an O2 molecule here. So we're going from solid to gas. That is a huge gain in entropy, but it actually requires energy in order to make this conversion, in terms of the bonds itself. So the amount of energy in bonds here is actually greater than over here. So when we convert from here to here, we need to convert some of that energy. Now, since we have such a big change in entropy, that is enough to supply that energy debt and still maintain a large negative delta G. So we can achieve a negative delta G utilizing multitude of different combinations of enthalpy and entropy. Something else to consider is the concentration of things. So if you remember this general paradigm, we have the reactants and the products, and we can write this into an equilibrium constant where we have the concentration of the products raised to the power of the number of moles, and we have products over reactants. That gives us our equilibrium constant. And that is utilized to glean certain pieces of information about a reaction. But what we need to consider is that if we start tweaking those conditions away from this equilibrium, then that can have a net effect as well. So if we also look at delta G in terms of, we've been looking at it in terms of the final G minus the initial G, but also we're actually dealing with products and reactants, right? So we can look at where the energy is coming from products and reactants. And here we start pulling in those equilibrium constants. Also keep in mind that all of the delta G reactions are all about standard conditions, right? And our body is not standard condition. So when we need to figure out what an actual delta G of a reaction is, we need to both take into account what the actual temperature is of what's going on and what the physical concentration of the product and reactants are. Since this has an effect on the overall delta G, we can actually manipulate a system on whether it is a positive delta G or a negative delta G simply by changing the ratio of products and reactants. And we'll see this happening in glycolysis. So our learning objective today is hopefully now you can explain how changes in Gibbs free energy determine the direction of chemical reactions.